And the second time, you say yes. So we could then walk into this, and then we have a little object called Tetris that will play the sound. We'll talk more about that. We have another function to clear the line, to get rid of it. Then another function to drop the line, which would take these lines and put them down one lower. And then two more variables. One to keep track of the number of lines that the person has cleared over the course of playing the game, and then one to keep track of the number of lines for that particular turn, just to do any cool processing or special effects that we want to have. And at the end of it, this nifty little modulus operator, which is basically just going to give me the remainder of the number of lines divided by 10. So if it's an even interval of tens, we then have another function that does the level up and speeds up the game. So this is like a pretty simple example of coding, and this is the type of stuff that we do. So now let's talk a little bit about the process, right? We know what the developers do. We have an idea of what the artists, the designers, the producer does. So how does this all come together and make the great games that we see every day? We start off in the process, well, all of it, I guess we should say, together is called the software development life cycle. So we begin with the specification. And that's where we decide, like, what exactly is it that we want our game to do? Again, with the example of Tetris, we want it to drop blocks. And the role of the developer in this is, in a lot of ways, is to be sort of the critic and sort of like the technical expert. To ask the question, well, you want to do all these things, but is this realistic? Is it realistic with the amount of time that we have to develop the game, with the hardware resources that we have, with the number of people? And also, are there things that you're forgetting? Are there more things that we can do if we have, a great network adapter that we can add multiplayer features to, if we can do cooler graphical or special effects? We think about those things during the specification phase. Then comes design. I'd say that design is probably the most fun part of the development cycle, because it's the part where you're not quite working, but you're kind of playing around and seeing what will work. And for developers, that falls into two categories. The first is, I guess, like creating what we call prototypes. So if we have an idea of a gameplay mechanic, instead of building it out in a fully functioning, working, shippable version, we'll just come up with a very simple example just to see if we give this to someone and they play around with it. Is it good? Is it fun? Is it worth continuing, or should we just drop it and should we try something different? And then comes the part where we create design documentations. Not all teams do this, but for larger teams it becomes more and more important. This is where we actually write essentially documents that are explaining, well, okay, I know that I want to create this feature. What are the functions that I'm going to create? What are the lines of code that I'm going to write that will make it clear so other people that are going to work with my set of code will understand and can work and write code on their own that will work naturally with it. Then there's implementation, and this is the meat of the development cycle. This is where the artists are creating all of the images, the models, the graphics, the sounds. This is where we're creating the code to create the virtual world. And you begin to see it come from the idea into the full fleshing out of a game. And usually, as I said before, if a game development cycle for a large title lasts somewhere between 2 to 3 years, we want to break this down. We don't want to just finish everything and then put it on on a disk and then give it to the test team and say, does it work? So what we'll do to break it down is have what we call milestones. And for each step, we'll say, okay, we want to have a certain set of features done with the graphics in place, with this much code and these many features actually working, and we'll hand that off to test, and if it's broken, we'll fix it as we're building and adding new things. Then there's deployment. This is the stage where we believe that we've been through all the milestones, the code works as expected, the graphics are in place, the sound is working, the game is, for the most part, done, and we just want to verify that everything is in place, that it meets the expectations of the original specification, as well as whatever requirements are placed on us by the platform holder. Traditionally, the Xbox, the PlayStation, the Nintendo Wii, they all have requirements of what a game on their system must do and must not do. So you're going to have to go through that phase during deployment. And then there's maintenance, and this is becoming a larger and larger portion of the game development cycle. When I was younger, you'd essentially buy a game, you put it on your computer, you play it, and you were done with it. But today, with the internet, it's expanded from simply just offering new patches to games to fix things that may have been missed during the development cycle. to adding new content, adding different levels, and adding different styles of play. So, at a high level, this is pretty much the game development process. These are the people involved and more or less what a developer does. So, the next question actually is a question I have for you guys, and as we move into how does this apply to the games that we're seeing today, what games are you guys playing? I saw everyone that raised their hand to play a game. What types of things do you find interesting? Halo, all right, I love that game. What else? Oblivion. Had trouble with that one, but great game, great game. Left 4 Dead, okay, a Valve fan. All right, let me get one more. Gears of War. One of my best friends actually worked on that game. So the reason I wanted to get out these names is that no matter what game you told me, you'd always have a couple of commonalities among these games and what developers are going to need to do. And I wanted to talk a little bit about those and then how they apply to math and science. So, like I said, we do code, and the core of code is mathematics applied. It's a good amount of physics. It's a good amount of like logical thinking, which is the cornerstone of being a scientist and being an engineer. So I thought of 3 examples that I think will probably hammer home things that are just prevalent in game development that require a math and science background. So let's start with optimization. The core of just about every game is what we call a game loop. And basically what happens here is we say while true, which means that we're going to keep running this until something that the user does breaks us out of it. We're going to read everything that the user does, and then we're going to update the world based on the input, and then draw it. And if the user does something to get us out of it, we'll break, and then that's the end of the game loop, and we quit. At a high level, this is what every game goes through. And it goes through it traditionally about 30 or 60 times every second. So you update all these things, you draw an image on screen, you repeat, you repeat, you repeat, so it gets that fluid animation that we're used to seeing. And what was great about my example of Tetris is that you can figure out everything that goes on in that short amount of time, draw it on screen, and you're fine. But you look at the games you're talking about, the Gears of Wars, the Halos, the Oblivions, they have these huge worlds, and you can't imagine a computer currently would be smart enough to be able to figure out all the graphics, all the polygons, and put everything in place and draw it in that short amount of time. So we need to find ways to do shortcuts. And this is where optimization comes in, and this is where math becomes important. So the example I have here is from one of my favorite games, Street Fighter. And if you look at the image, you see the guy doing the dragon punch, and he's knocking Blanca back. But what you don't see is the letter E in the word diner. And that's because, obviously, from the position of the camera, he's blocking it. So this is where developers use a technique called occlusion culling, which is a big fancy term for if you can't see it, don't render it. So if it's occluded, blocked, cull it from our list of things that we're going to draw. And to do that, basically we have an algorithm where we take the point of the camera and draw lines into the world. And anything that has a polygon from something else, like that sign, that's blocked by a character, we know that it's never going to be seen, so we don't worry about it. So we cut down the set of things in that drawing step to enable us to get through all the things that will actually be seen. So that's one of the techniques of why math is important to us.